guys, welcome back to TechDose, and in this video we will look at count the number of powerful integers, which is from Leetcode number 2999. Let's now read the problem statement. In this problem you are given three integers start, finish and limit. You are also given a zero indexed string s representing a positive integer. A positive integer x is called powerful if it ends with s. In other words, s is a suffix of x and each digit in x is at most limit. Return the total number of powerful integers in the range of start to finish. A string x is a suffix of a string y if and only if x is a substring of y that starts from some index including 0 in y and extends to the index y dot length minus 1. For example, 25 is a suffix of 5125, whereas 512 is not a suffix, right? Now let's look at an example. In this case, we are given the start point as 1 and the finish point as 6000. Our limit of digit that we can take is from 0 to 4, not exceeding 4, okay? And s will always be following the limit for every digit. That means any digit in s cannot be greater than the limit, whereas the start and finish will not be following the limit, okay? They can have any digit from 0 to 9. Now in this case, we are asked about finding out how many numbers exist between start and finish, including both the numbers, in such a way that 1 to 4 is a suffix. Now if I can tell you such number, then you can say that 0, 1, 2, 4 is such number, right? So you have to ignore this 0 because it is insignificant. So 124 will be such number. Or I can say that I can place a 1 here and I will say 1, 1, 2, 4 is one number, 2, 1, 2, 4 is such number, right? So likewise, if you generate the numbers, then you will get a count equals to 5. Okay, so that is why 5 is the answer here. Now, if you look at another example, then in this case, I want to find all the numbers having suffix equals to 10 given from start to the finish point from 15 to 215. And each of the limiting digit should not exceed 6. So in this case, what I can do is I can find all the numbers having 10 as a suffix from 1 to 215. And then all the numbers which has 10 as a suffix from 1 to 14. And if you get an x count here and a y count here, then since I want to find from 15 to 215, I can just do x minus y and return the result, isn't it? So writing a single API of how to find the count of all the numbers from 1 to any given number, any given positive number having the given suffix, if I can write such function, then I can easily solve it in two parts and get the result x and y and just return the subtraction of the value, right? So this will be the idea which we will be following. But before looking at any solution, let's look at the constraint. In this case, the start and finish value is maximum 10 to the power of 15, which is approximately a 16 digit number, right? So if you are trying to get enumeration of all the numbers from start to finish, where in the worst case start will be 1 and finish will be 10 to the power of 15, it will definitely take 10 to the power 15 operations minimum, right? And on top of that, you have to analyze all the digits as well. But I'm not counting that. This is way greater than your 10 to the power of 8, right? Since I want to run this algorithm within 10 to the power 8, so I cannot do such kind of thing. Even if I would do in square root of 10 to the power of 15, then that will be approximated to be 10 to the power of 7.5, or you can say 8. So I have to do something even better than square root of n, right? And you can assume that I have to solve this problem in log order, simply log of n order, where n is actually the finish, right? So this should be my time complexity expectation out of this problem. Now once you know what to expect of this algorithm, then it will be easier to think the solution in such lines, isn't it? So the limit value is from 1 to 9, okay? And the s dot length, which is the suffix length, will always be having the maximum number of digits less than equals to the finish number, right? So there will never be a case where the suffix asked is having more length than what the finish value is given. But this does not mean that the finish value cannot be smaller than s. You should always take note of this, because the finish value can be 1, 2, 3, 4 and the s value can be 5000, and I will be asking you to find from start can be anything which is less than equals to finish, right? So I can ask you about find the count of numbers which has 5000 as a suffix given from start. Let's say start is 1 1 2 1 2 3 4. So the count will always be 0 because the finish value is actually less than the s value, right? So I'll show you all these boundary cases, but from this don't assume that it is saying that s is less than equals to finish. No, it is just saying that the number of digits is less than equals to the number of digits in finish, but that does not imply that s is less than equals to finish. Fine. S is only containing numeric digits which are at most limit, and S does not have leading zeros. Fine. Once we have understood everything, let's now look at some observations. So according to what we have studied, start is less than equals to finish, I can say, because that was already mentioned in the constraint, right? Start is less than equals to finish. But S may not be less than finish, as I explained earlier. And start also can be either less than equals to or greater than S. The second point is any digit s at I should be always less than equals to limit. This rule is only followed by the numbers that we will be generating and s, but this is not necessarily true for start and finish. Fine. So the start can be like, let's say 142, finish is 24638, while the limit was only 4, and the s value will always have all the digits within the limit. And whatever number we will be generating from start to finish having suffix s should also have all the digits less than equals to limit. That we should take care of. Now the maximum number will be no more than 16 digits, as it is mentioned maximum number is 10 to the power of 15. Now once you have understood some constraints, let's look at an idea. In this case, if you are given start and finish value with the limit value being 7 and s value being 10, our goal is to find all the numbers from start to finish with s as the suffix that you know. So we need to enumerate all the values greater than equals to start and less than equals to finish. So that enumeration can be 110, 210, 2110, 410 and so on. So as I already told you that you can actually count all the numbers from start to finish by counting all the numbers from 1 to finish and subtract from 1 to start minus 1. So this is your x value, this is your y value, as I said, and x minus y will give you the count of all the integers in the range of start to finish inclusive of both the values, which will have s as the suffix. So in this case, if you take count of 15 to 2134, then you can take count from 1 to 2134 minus 1 to 14, and you will get 18 minus 1, which is 17. This is a simple idea, right? Now I'll keep telling you about the boundary cases. There are multiple boundary cases for this problem. In this case, if the start value happens to be less than s, okay, start value happens to be less than s, like let's say the start is 8 and the s value, that means the suffix should be 10, then does it even matter that I will be counting the numbers from 1 to start minus 1 where the suffix will be s? Well, the suffix will never be s. This count will always come out to be 0 when the start value is less than s, right? Because you have to have a number at least greater than equals to s to have s as a suffix. You cannot have a smaller number than s and say that I will have s as the suffix. That is not going to happen. So this is one boundary case where I will say that if start is less than s, then counting from 1 to start minus 1 will always be 0. So I will not calculate it. Rather, I will just return the answer from start to finish as 1 to finish simply. And you just return the value x as the answer, right? But if finish is less than s, then you can imagine that the count will always be 0 because s can never be a suffix. I showed you that example while reading the question, right? That finish can also be less than s even though the number of digits can be same in the worst case, right? So in that case, I will not calculate anything. I will simply return 0. So I think this idea is clear. Now let's see like how to generate the numbers digit wise, what we should take care of. While we are generating the numbers, limit is important because I cannot choose any digit which is exceeding the limit. But limit is not the only thing that I should take care of. Actually, I will be looking at the start digits and I should not exceed the limit, yes, but I should also not exceed the corresponding digit. Otherwise, I will be exceeding the amount that I should actually look at, right? So let's say that this is not start, but this is finish. Let me just assume that it is finish. And I want to calculate all the numbers from 1 to finish. All the numbers from 1 to finish where the suffix is always equals to 21, as given in this case suffix is always equals to 21. So how to generate such numbers? Now for creating the numbers, I will assume that it is a 5-digit number from 0 to 4. So for the first digit here, the options will be always minimum of 2 comma 3, minimum of whatever you are looking at s at I comma the limit. That is a sensible choice to make, because if I am generating all the numbers from 1 to finish, then I cannot generate anything which is greater than finish. While if I had taken an option 3 here, thinking that limit is allowing me to have a 3, then as soon as you place 3 at the most significant digit, then this number will definitely, whatever you put here, it does not even matter. It will exceed the value finish. That I do not want to do, right? So that is why, since I do not want to exceed finish, I will be taking the digit option as minimum of the current digit comma the limit. If this digit was, let's say, 7, then still I cannot take from 0 to 7, because the limit is not allowing us to take 7 or maybe even anything after 3. That is not how the problem has been framed. Okay. So I'll always take minimum of limit comma the current digit, and that is 2. So how many options do I have here? I have 0, 1, 2 as an option. 3 options are present, right? Now if I move forward to 1, for whatever you had chosen here, what can be the options for this one? Now if you carefully think about it, if you had not chosen this 2, let's say, then you had chosen 0 and 1, then I can select any number from 0 to limit simply. I can choose here 0, I can choose 1, I can choose 2, I can choose 3, but definitely I cannot take any digit greater than the limit. And even though this value was 1, because if you had already taken a smaller digit for a significant digit, like if I had taken a 0 or 1 as the say on the significant side, that is to the left of this digit which I am trying to fill, then I can safely exceed the s at I value. Okay, this is your s at I value. So I don't need to be barred from s at I. If I had taken a smaller number on the left side than the actual s at I, then I have the luxury of choosing the number from from 0 to limit. And that is what I'm doing. But if you had chosen 2 here on the left hand side, that is actually matching up with the s at I, then the next number should be taken as minimum of 1 comma 3. These are the two cases that you will see. Okay, so if you had chosen any one of this 0 or 1, I will be ending up with 4 options from 0 to 3, that is from 0 to limit. But if you had chosen 2, then you will only have 2 options, which is 0 and 1, which is the minimum of this 1 comma 3, right? So I have already enumerated this case that I will be managing this with a Boolean variable is tight. So this tight variable will tell me if I had actually used a digit which is equals to s at I every time on the left hand side, So if is tight is false, this means I have the luxury to choose the current digit from 0 to limit. Whereas if the is tight is true, that means I have already chosen a 2 on the left hand side, so I have to choose minimum of limit comma start position. And this second case should always hold true for the first digit. Whenever you start, you should always start with the tight limit. Okay, so that tight limit will always be true for the 0th digit, and depending on what you have filled here, it will be propagated to the next digits. Now let's say that you had taken a 2 here, so the tight value was already true and you have taken a 2. So for the digit number 1, the tight value will be true as well, right? Now I have only 2 options, 0 and 1. Now let's say you have taken a 0 here. So the tight value will become false for the second digit. And after that, you can choose all possibilities, but not going to 5. This 5 is of no use for us. I will take only from 0 to limit if the tight value is false. From 0 to limit, right? Because I cannot exceed the limit, so I will try to utilize 0, 1, 2, 3, 4. 0, 1, 2, 3 in such case, right? But if I had chosen 1, then the tight limit will not be false, but it will be true. And so I will be taking the options minimum of 3 comma 5, which will still come out to be same in this case, right? But let's say that the tight value was true here, and then it became false here, because you had chosen a 0. So after this, once the tight value becomes false, the tight value will always remain to be false. Whatever option you take, it does not even matter. Because once, let's say, you had taken the 0th digit to be 2 and the first digit to be 0. After this, it does not even matter what digit you are putting, as long as these digits are within the limit. Because this number starting with 20 will always be less than the number starting with 21. Okay, so as soon as you break the tightness constraint and make it false, it has started with true, but if you make it false, then after that you have to always take the options ranging from 0 to limit. Okay, if you did not understand this, please pause it and rewind the video and again watch it back, right? So using this idea, you don't even have to go with recursion, dynamic programming and all these solutions. I'll show you why it is a DP solution and recursion. But what you can do is you can simply use maths, because you can just take care of the boundary cases, which I will be telling. Some of them I told you, some of them I'll be telling you. Take care of that and you keep multiplying the possible options that you can put. But I will not be going with the math solution, because this may not be very easy to understand for most of you guys, and I think it will be too much of an overkill. So I will be just doing the standard algorithmic solution for this problem. Now there are 3 questions to discuss in this scenario. What is the range of the digits at each index? That I have already explained you how to take care of that using the is tight, and how to track what should be the range. So the tracking should be done with the is tight variable, which is a boolean type, and how to guarantee that the suffix s is generated. Now this one I didn't tell you. Let me tell you now that how to guarantee that you end up with the suffix s, whatever is the s value. Because I cannot just keep on generating all possible numbers, because that will just be like a for loop, right? If I had run a for loop from start to end, then that would be same as whatever method I'm telling you right now. There is no difference to it. And this is a recursive method, and the iterative method is already taking a lot of time. So what I will do is I will find the size of this s. The size of this s is 2. That means 2 digits are present, right? So as soon as I reach to that index, as soon as my current index is reaching to the second last digit, right? Second last digit, because the size of s is 2. If the size of s was 3, then I would say the third last digit. I will show you in the code how to check that out, but I think you can do that easily. So if you reach to the second last digit, then you do not apply your options. Okay, then we will not be taking a minimum of limit comma start or 0 to limit. No, none of these options are going to run. I will be simply forcing this second last digit to be 2 and the last digit to be 1. There is no option for this digit 3 and 4. It has to be 2 and 1. Okay, it is only having one option, because I will always be generating a valid number, and a valid number is 1 where all the digits are within the limit, and the second condition is the suffix should always match with s. Now how do I know that whatever, if I'm forcing this 2 and 1, then it will be following that all these digits will be always less than equals to limit? Well, it was already mentioned in the question that each of the digit s at I will always be within the limit range. You see, s only contains a numeric digits which are at most limit. So if I am forcing them to be 2 and 1 because I want to match the suffix, then they are already following the limit. Okay, I don't have to check for it. So that is how I will be guaranteeing the suffix x is generated. Okay, so the suffix will only have one option. So the options will only rotate for the prefix which do not include the suffix, right? They will only create so many possibilities that you need to count. So I think you got an idea of how to generate the numbers digit wise. Now once you have got that idea, let me show you a recursion tree diagram of how to use recursion to generate the numbers. So I will be taking a limit value 2, and let's say the s value being 21. I have taken a start value to be 1432. So maybe I want to generate all the numbers from 1 to 1432, or you can say that this is my finish number. Anything is fine, right? So I have a 4-digit number. Now you think about this position 0, 1, 2, 3. This is position 0, 1, 2, 3. How many suffix items do we have? We have 2 digits. So this will go to the suffix side. Okay. Now once you are not at the suffix side, then how many options do you have right in the beginning? You check it out. at this 0th position, since the tight value will be true, because you will always be starting with the is tight value true, the option will be minimum of this digit 1 comma limit. So that will be only a 1, so you can use 0 comma 1 here. So you have two options, either you use 0 or you use 1, that's it. So that is why at position number 0, this is not a number, this is just a position, right? So at position number 0 you have two options, 0 and 1. Well, if you take the 0 option, then you know that the is tight value will become false, because you have started with the digit which is smaller than the digit which is present in the finish number or the start number, right? So as soon as you put a 0 here, the tight value will always be false for all the subsequent nodes, no matter what you put. Okay, because you have already put a 0, so the number is going to be smaller than whatever is the given number, so you are not going to exceed that anyway. So the tight value becomes false as soon as you pick a 0. Now at position 1, the option will only depend on limit, it will not depend on SAT because the tight value is false. So I'll be going from 0 to 2. That means I can pick 0, 1 or 2 at this position, 0, 1 or 2, having picked this 0. Okay. Now if I have done that, then I will be going to index 2. Now at this point, nothing matters, tightness and nothing matters at all. At this point I will be forcing the value to be set as 2 comma 1 at index 2 and at index 3. So at index 2 and 3 I will have only one option coming out. You see, I will exactly have one option coming out, and therefore this will give me one possibility, right? So what is that number? 0021. 0021 is one number, right, which is in the range of 1 to finish, you can say, right? So this is a valid number and this will be contributing +1 to our count. And then we will be backtracking. So when we backtrack, we will be backtracking from the suffix items altogether and go back to index 1, because there is no other branching for any of the suffix indices. It just had one option. So from 1 you can try to put the other option, that is 1, right? So if you put that, then the rest of the two options will definitely be your own 2 comma 1, that is fixed. So this will also contribute +1 to our option, right? This will also contribute +1, and then you have tried all possibilities. From 1 you go back to 0. Now at 0, if you had put a 1, then for the next time you will have to take the minimum of 4 comma 2, which again happens to be 2 itself, right? So you will have 0, 1, 2 as 3 other options, and so this will contribute +1 +1 +1 to the count, and therefore the total count of numbers where 21 is the suffix and you count from 1 to 1432 will come out to be 6 only. Okay, so I think this is clear how to generate all the numbers using recursion and using the is tight as your boolean type to say what will be the range of digits that you can use. Will it be from 0 to limit, or will it be from 0 to minimum of limit comma SAT? Fine. So once you have understood this, then let's look at the special boundary case. In this case, if you have the finish value is, let's say, 2632 and the limit value to be 8, where s is equals to 35, then you will end up with a number where you choose a 2 where the is tight value was true. Then you go and put 6 where the is tight value was true, and then you are forcing to put 3 and 5 at the end, because we are not checking anything at the end. That I'll be showing you in the code. So if you happen to force a number like this 2635, then this will get counted, but this is actually outside of your range from 1 to 2632, and so this is invalid. This is a case where an extra counting can happen because we are forcing the numbers at the end. Okay, so this happens only when the tightness on the left hand side, leaving the suffix items, for all the digits on the left hand side, that tightness always happened due to SAT. That means all the digits in the finish or all the digits in the start, whatever we are calculating with, right? The tightness never happened due to limit, but it happened due to the digits present in the finish or the start. So if that is the condition which happens, then you will end up with a number which will be greater than the finish value, which does not fall in the range, and so it has to be subtracted by -1 value simply. Okay, but this condition will never arise if the suffix of the finish is greater than equals to s, because if this was, let's say, 38 instead of being 32, then do you think that 2635 will be outside of range? It is not going to happen. Okay, so this condition arises only when two things happen together, that is the suffix of your given number, finish or start, whatever, the suffix of your given number is less than s. That is the first condition. And the second condition is all the numbers on the left hand side, all the digits on the left hand side are actually less than equals to limit. If that is the case, that happens, then this overcounting scenario will happen, and it will happen only once. Okay, so this has to be taken care of by subtracting a -1 value. So this check has to happen. So I'm just reading out my statement. This will work only when the suffix of finish is greater than equals to s, provided limit do not cause tightness, that is limit is greater than s at I. This will work if the limit is equals to 5 even, because the tightness using limit was applied on at least one digit. Because if your limit value was 5, then you could not place a 6 here. You have to place a 5. And so this 35, 2535 will always be within the range of finish. You have to think over it a little more carefully, right? Therefore, we need to adjust this case by subtracting 1. You have to check this case separately, right? So I think it is clear. Now once it is clear, let's look at the optimal recursion memoization using dynamic programming approach, right? I will be showing you why this is dynamic programming as well. In this case, I have taken just a simple example from 1 to 2332, and I will be trying to calculate how many numbers are generated from 1 to 2332 having the suffix 33 with the limit value 4. Once you learn about how to calculate from 1 to 2332, then you can just repeat that process from 1 to start -1. But start equals to 1 is a special case where from 1 to 0 it does not make sense, right? So when start equals to 1, then you just calculate from 1 to finish, and that's all. That's the count. Fine. Now in this case, I need to generate 4-digit numbers, right? So I will be taking options of 4-digit 1, 2, 3, 4. Now if you look at it, this is 0, 1, 2, 3 as the positions. Now I have the first digit with the tightness value true. That is where I will be starting with tightness value true. Okay, these are all the positions that I have marked in the node. Since the tightness value is true, I have to consider the minimum of 2, 4, which will be 2. So I will have 3 options here, either to place 0 or 1 or 2, and that is why there is 3 branching 0, 1, 2. Now if you pick any of these 0 or 1, the tightness value is going to be false, and as soon as tightness is false, the entire subtree will never have tightness value true again. It will always be false, because a significant digit became lower than your finish number, then that means it is never going to exceed that number. Okay, so this entire 2 subtrees will always have tightness value false, and hence I will not be writing it again. So let's say that you place a 0 here. So what will be the option at this position number 1? It will only depend on the limit. It will not depend on this 3. Okay, because the tightness is false. So I will be putting 0, 1, 2, 3, 4 as 5 options. Okay, so at 1 I have 5 options, and hence we have 5 branching. Now for the last 2 options, that is 2, 3, since it is the suffix part, right? I will be forcing the numbers 3, 3, which is in S. I have to force it. So at 2 and 3 there will be exactly one option, and that is why there is exactly one branching. So all the possibilities will occur only due to index 0 and 1. Index 2 and 3 do not contribute to the count of possibilities. Fine. So if you follow this one branch, then this will contribute +1 to the count. Okay, +1 to the count. I am just showing you the recursion approach right now. Then here you will have +1 to the count, +1 to the count. What is this second number? This number is 0. You had put a 0 here, right? And this is 0. Then this will be 3, 3. You see this, I have already written 3, 3. So this number that you get is 0, 0, 3, 3. This is within the range, and it is fine. Within the range of 1 to finish, right? Then this number is 0, 1, 3, 3. So 0, 1, 3, 3 is also valid. This number is 0, 2, 3, 3. So you see how the numbers are getting generated. This number will be 0, 3, 3, 3. This is also +1. Then you have 0, 0, 4, 3, 3. 0, 4, 3, 3, and this is also valid, right? So you keep adding +1 like that. So how many count did you have right now? 1, 2, 3, 4, 5. So I have +5 count by branching from 1. Okay, now if you go back to this 0 after branching and you again make a call to this 1, then this means that at 0th position, since you had put a 0, now you are trying to put a 1. So the tightness value will still be passed as false, because at 0th position you have 2 as the digit value, and anything below 2 will be making the tightness as false. So if you have tightness at false, then in how many ways you can fill these 3 digits in such a way that 33 is the suffix will be the same as how many you had generated placing 0 on the left, because whatever you put in the left has no significance provided the tightness value is the same. That means other than 2, if you place 0 or 1, it does not matter. For 0, whatever was the count of combinations, for 1 also it will be the same count of combinations. And that is how you could also solve this problem with maths, simply by combinatorics, multiplying the number of possible combinations, right? So that is why I will say that this is a repeating subproblem, because the subproblem in this case is defined only by the position as well as the is tight value. Is tight value, either it is true or false. Because if it is true, then I will be taking the digit as minimum of limit comma set I. Otherwise, if it is false, then I will be taking from 0 to limit. So this is affecting our number of combinations, and position is affecting because given the position, it will define how many digits I have, right? So position comma is tight will only define our subproblem. So if you see here, the position for all these 3 are 1, but here the tightness value is false, and here also false. But here it will be true, because if you put a 2, which is the limit, I mean it is equals to set I, then the tightness value will be true. So this one and this one are the same repeating subproblem, but this one is not repeating. Okay, this is a different subproblem. So similarly, I will be just returning a value 5, because I will be saving it somewhere, right? So I can simply make a table, a DP table of size, position, and you know that this is a 16 digit number, so I can simply take 17 size, which is from 0 to 16, and the tightness value can no more be true and false, so I will be taking DP of 17 by 2 and pre-assign it with all the -1 values, because I know that all the numbers are positive here and the counting can never be negative. So if I put a negative number, then I can say that if I want to get the solution for the sub problem, let's say position number 1 and the tightness value being false, which is 0, and if it says that it is already -1, this means this is not calculated, and you need to calculate it. The first time you calculate it, we will be filling up this value with the count, which is 5, and the next time when I see the same sub problem, I will be simply returning 5. So the value that you get at 0 is 5 plus 5, which is 10. Now for 2, this value is true, right? This value, the tightness value is true. So this is a different sub problem. This sub problem is 1 comma 1, and this value is still -1 in the DP table, or you can say the memoization table. Okay, now since this is not yet solved, I will be solving it. And so at the first index, when the tightness value was true, that means you had put a 2 on the left hand side. What all options I have at index 1? Index 1 has value 3, right? It has index 3. So I mean the digit value is 3. So I can put 0, 1, 2, 3, which is minimum of 3 comma 4. So initially I had 5 options, 0 to 4. Now I have 4 options, 0 to 3. So you see the branching is only 4. Here the branchings were 5. So you have 4 branching, and as soon as you pick any of these values 0, 1, 2, 3, I mean let's say you put 0, 1, 2, you are going to the suffix index, and at suffix index you don't have any option, but you have to just force yourself to put 3 comma 3, right? So this will be giving you +1 count, +1 count, +1 count, +1 count. Even the tightness value wouldn't matter when you go to the suffix index, because at this point you just have to force yourself to put the value, and I already proved that this will be always within the limit, because all the set I is less than equals to limit. So that is why you can just force yourself to put 3 comma 3. So now you have got a 4 count here, so you can overwrite this to 4 and you will be returning the value. Okay, so this value is coming out to be 14, but in reality here the value should not be 14. The actual value should be 13 only, because I showed you the boundary case about overcounting. So here what is happening? What is this last number? If you see 2, 3, 3, 3, this is 2, 3, 3, 3 as the last number. But if you see the finish value, it is 2332. So I'm exceeding this value, right? So this should not have been counted actually. So after doing all the counting, whatever count you got, maybe this is correct, or maybe you need to get one less value which will be correct. Any of these two values will be correct. So you have to check for correctness. I told you about two criteria. You have to check the suffix value. The suffix value 32, if it is greater than equals to s, then you don't need to do anything. It is fine. But you see that the suffix value 32 is less than 33, which is the s value. So that means there is a chance that we might have to adjust a -1 value, because there might be a chance of generating a number outside of the finish range, and that I have to check with all the prefix items, leaving out the suffix value. All the prefix items, I have to check all the digits. If all of these digits are always less than equals to limit, then there is a chance that you will be able to generate a number which is outside of the range of finish. And yes, it is true in this case. 2, 3 is always less than equals to 4. So that means I have ended up with one extra count. So I will be adjusting it with -1. And so my actual answer will be 13. And that is how the answer will be 13 here, right? So I think this idea is clear. This is also called your digit dynamic programming, because this is dynamic programming applied on digits. Fine. If you are good with recursion, then this will be easy for you to understand even. Now, having understood this, how many subproblems will be there? You know that in the problem statement, it was mentioning about 16 digits, and 16 digits with simply two tightness constraint, true and false. So I have taken 17 by 2, so it will be 34. So maximum unique subproblems will only be 34. But even though problems are unique or not unique, the maximum branching that a node can have is 10, which is from 0 to 9 if the limit value happens to be 9, right? So considering all those cases, your number of subproblems will be maximum digits into 2, which is the digit is counted by log base 10 of the largest number, and let's say that largest number is finish number. Let's assume that it can also be s, right? But that boundary case I will already be handling if I even need to solve it. So I will always take finish as the largest number. So log of finish base 10 would be like the number of subproblems in this case. Multiplied by 2 definitely, due to the tightness. And the total recursion tree node will be total number of subproblem and the options per node. So you can have 10 digits, so 10 options per node. All these are constant, so you can assume like log of finish will be the time complexity, and the space complexity will also be same, because even though it looks like a two-dimensional table, it is just a very simple size table, which is log of finish, right? 2 times log of finish. So I think we have understood the entire solution. Let me know in the comment section if you have followed the digit dynamic programming or the maths combinatorics method to solve this problem. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the start, finish, limit and suffix. So I will be using the stole function, which is string to long integer in C++. Okay. You can check out in your language how to do that. I have already provided Java and Python code. So I'll be using stole everywhere because it is easier to compare two integer numbers or long numbers rather than comparing two string. So string to long on the suffix will give me the suffix value, and I will convert finish to string called finish str, and start -1 to string which is called start str. Now find the number of digits. You can use this formulation, or you can take the log base 10 of the finish number and +1. This will give you the number of digit which is the same as finish digit and start digit. So these are the two ways you can follow anything. So this seems to be a less complex method, so I have followed converting to string. Now I will be calculating the count of all the valid numbers from 1 to finish in up to finish, and 1 to start -1 in up to start. but I will only calculate up to finish if the finish is actually greater than equals to suffix value. Otherwise we will always have 0 as the answer, right? And the same goes for start. I will always calculate from 1 to start minus 1 if the suffix value is less than start. Otherwise, if you do not have any count, you already know it will be 0, then why don't you just replace with 0? Why are we solving it, right? So I have written a utility function here, solve up to, so that I don't have to write it 2 times. Okay, otherwise we would have to write this piece of code 2 times. So in this particular case, I'll be calling solve up to finish string, finish digits, limit suffix. Similarly, start string, start digits, limit suffix, right? So let me show you these 2 pieces of code. So the first utility function is your solve up to. In this case, I will be setting the DP table to -1. As I said, the count will be -1 initially, and taking the count value in result. Then I will be checking if an adjustment by doing -1 is required or not required, and accordingly I will be sending the result back. Now the adjustment code is written on top, but before seeing that, let me tell you about the digit DP. So this is the application of your recursion code with digit dynamic programming. So in this case I am getting the number, the current index that I am looking at, the maximum digits that you have in your given number, the is tight value, the limiting digit, and the suffix that you want to match up with. So if the index reaches to max digits, that means you are out of bound, then you return a value 1, because we have reached to the end of the recursion tree diagram at the leaf node. So we have generated one valid possibility. I have already shown you in the recursion tree diagram, if you reach to the end, you will add +1. That means you will be returning a value 1 simply. And if you have not reached to the leaf, then if this subproblem has been solved already, then you return the answer without solving it back again. Otherwise, if it is the subproblem where you are reaching for the first time, then you will be looking at the low and high value. This low and high value will tell you if you are trying all possible digits at a point, from low to high you have to try. Okay, so the low will always start at 0. Fine, the suffix length is the suffix dot size simply, and I will be checking if the index is actually in the range of the suffix, because these all may be the indices and the last 2 digits may be the suffix. But how will you identify? If the index is greater than equals to max digits minus suffix length, that means you are inside the suffix index. That means you are at the end part of the indices. In that case, you have to see what is the suffix index. So the suffix index will be calculated simply, and after that the low and high value will be set exactly equals to the suffix, because then I cannot iterate. If the suffix has to be 3 here, then it has to be 3. So the low value will be set to 3 and high value will be set to 3, because if I try using a for loop putting all possible digits there, then it should be only one possibility. We do not want to try any other possibility, right? So that is the reason we have set this value like this. Otherwise, if we are not at the suffix indices but we are on the left side of the suffix indices, then the high range will be decided by the is tight, because if is tight is true, then that means I have to take the minimum of limit comma s at I. Otherwise I have to take just limit as the high value. After coming out, I will be calculating the total possibilities at a given node, and I will be trying all possible digits that I can place at a certain index, right? I will try that out. So I will try it out using a for loop, and I will always be calculating what should be my new tight index, because if my limit is from, let's say, 0 to 4, if I place anything from 0 to 3, the next recursion call should always have the is tight value as false. Okay, so that is what I will be doing here using an AND operation. Otherwise, if the is tight was true here, and this 4 is also coming because of the tight value, then actually I should be sending the is tight value to be true even forward in the next digit, right? So that is how the new tight value will be calculated, and I will be adding the total possibilities for each of the digit positioning, and after that I will be returning it back. But before returning, I will be saving it into the DP table, because the sub problem has now been solved. Now, checking back to the subtraction case, I told you that if you have a certain suffix, let's say it is 32, and the number that you are trying to place, like let's say s was equals to 38. Now if this suffix was somehow, let's say it was 42, it was greater than equals to s, then it is fine. You do not need to adjust anything, right? So this first check here, boolean subtract. Do I actually need to subtract? So if the suffix of the number here, suffix of the number, if it is less than the given suffix, then yes, then you might need to check the prefix items. Otherwise, if this 42 is already greater than equals to 38, then you will just return 0. That means you will return a false value. I don't need to subtract. But in this case, if it is 32, then 32 is less than 38. So the boolean subtract will be set to true. And if it is true, then we will be checking all the prefix items. Now, if it so happens that you have 2, 6 and the limiting value was, let's say, 7, or it can be 6, it can be anything greater than equals to 6 for this particular example. Now, if any of these digit values are actually greater than the limit, that means if the limit was from anything from 0 to 5, then at least one digit is greater than the limit. In that case, this subtraction is not done. Otherwise, if it is from 6 to any other number, 6 to 9, then for this example we need to adjust the value. You may have to enumerate and see for yourself how it is working, right? So this is the entire piece of code, and I hope it is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of this programming videos. See you guys in the next video. Thank you.